Hey guys, so momentum level 4. We're just going to talk a little bit about the basics of momentum. Talk a little bit about the definition, and then we'll talk about center of mass. So the basics of momentum. So going back, we have a Newton's second law. All of this matches the notes file, by the way, posted right before this. So you can read through the notes while I'm talking. It's kind of what I'm doing. So the basics of momentum, and momentum will use the letter P, and it's a vector. But thinking of Newton's second law, that the sum of the forces is mass times acceleration. When Newton wrote this, he actually said that the sum of the forces was going to be the change in the mass times the velocity over the change in time. So a little different. It's since changed, over the years, and we just take it for this. But the thing is that this right here tells me Newton's second law in terms of momentum, where this quantity on the inside, this is going to be the momentum. And so what we have the momentum P is going to be the mass times the velocity. And this is a vector quantity, so we need to pay attention to the direction of it. And this comes from our general understanding in day-to-day life. Big objects, lots of mass, lots of velocity, lots of momentum. Small objects, so little mass at low speeds, little momentum. And that's it. It's pretty straightforward. I think this is on your equation sheet. This is the next one. If we rearrange this, though, so if I just multiply that delta T over to the other side, so then we get the net force times the change in time, and that's equal to the change in momentum, mv. This quantity over here, this is the impulse. It's called the impulse. So the impulse changes the momentum. Let me fix that. Impulse. So the impulse is a change in momentum. So if we apply a force for a period of time, that's going to change the momentum. And that should make sense, because if we go back and we think about what happens when I apply a force creates acceleration, which changes the velocity, therefore changing the momentum. See, it's all connected and tied together. But impulse we'll talk about in, I think, 2 sublevels. So right now we're just focused on momentum. Pretty straightforward, just calculating it. And so I guess we can go through an example. So there's one in the notes, so let's do something else. So say, what's the momentum? What is P of a, we'll say, I don't know, 120 kilo linebacker running at a velocity of 4 meters per second. So pretty straightforward. The momentum is going to be the mass times the velocity. So momentum is going to be 120 times 4, which is 480. And that's the momentum. And these would be kilogram meters per second. So that's momentum. That one's straightforward. So we'll be asking other questions. What happens if this doubles? And even that's straightforward. If the velocity doubles, the momentum doubles. If the mass doubles, the momentum doubles, and so on. But we'll be doing some comparisons. Just want you to get used to the idea of it right now. So going on to center of mass. So let me get a new one. Center of mass file. Give me 1 second. So center of mass. You should kind of know what it is. It's kind of the balancing point of any object, center of mass. So it's the point at which I would follow the movement. For instance, you guys like to do that water bottle flip thing with some water in it. So we have a little bit of water. And what happens when you flip that thing and it's like rotating, right? And then it's going to land. The thing is if I find the center of mass, which in this case would probably be down here somewhere. I'm just eyeballing it. That center of mass doesn't do these flips. That center of mass does a nice parabola right through it. So it makes it easy to analyze these more complicated situations. So we want to be able to determine center of mass. It's just an easier way to talk about it, especially when we start talking about systems and say like a binary star system, where you have two stars that are orbiting. They're orbiting each other, but then they're moving, and so they rotate around. So then we can just all we have to care about is the center of mass. We can analyze just that point. We don't care what's going on around it. Anyway, so to determine the center of mass, it's pretty easy. If I want to know the position of it, the x of the center of mass of a system of objects, that's going to be the m1. So we take the mass of the first one times its position, plus the mass of the second one times its position, plus, oops, that's a 2, plus the mass of the third one, position, and so on. I can do that as many times as I need. And what I do is I just divide that by the sum of the masses. So I add mass 1 plus mass 2 plus mass 3, etc. And that will tell me the position of the center of mass. And so this would be in the x coordinate system. We can do the same thing in the y, and then you could combine them. So you could do, say I had a 2 mass object. Say the mass is 2, and we'll say its position is going to be 1, 2. So what we're talking about is on a coordinate system. So I'll go to 1, 2, and then I have a 3 kilo mass at, say, 5, 6. Well, then I can find the center of mass, and this is a little heavier, so it should be somewhere up in here, but let's go ahead and calculate it. So my x center of mass would be mass 1, so 2 times its position, its x position, so times 1, plus mass 2, so 3 times its x position, 5, and then we divide that by the sum of the masses. So that would be 3 plus 2 is 5, and then we get, that's 2, that's 15, so we get 17 over 5. Which would be what, 3 2/5. Okay, then we do the same thing with the y. So the mass times the y coordinate, 2, and that's coming from right there, plus the mass, 3 times 6, divided by the sum of the masses again, 5. So we get 4 plus 18 would be 22 divided by 5. So we get 4 2/5. 4 2/5. So my coordinates of my center of mass are going to be 3 2/5 and 4 2/5. So let's see, this was 5. This was 1. So there's about 2, 3, about 3 1/4, and then we'll go up. That was 2. This is, I'm sorry, that was 2. This is 6, and it's 4, so it's somewhere right in here. That would about be my center of mass. Anyway, that's how you can calculate it. What we'll be doing more of is the velocity and determining the velocity of the center of mass. So let's do that. It's very similar. Sorry, let me get a fresh sheet open. I don't know if I included that in the notes or not. Anyway, let's say we have an object, a mass of 5, and it's moving with a velocity in this direction of 2 meters per second. And let's say its position was 1. And then we have a second mass. So this is 1, this is 2. Mass of 3, its position is 5, and it has a velocity of, let's just say, 4 meters per second, moving this way. So, you know what, let's do the momentum. So let's do the momentum of this one. So the momentum of 1 would be the mass times velocity. So we get 5 times 2, so that would be 10, would be the momentum of 1. And let's see, this one has less mass, but it's moving faster. So let's check the momentum. So the momentum of 2 would be the mass 2 times the velocity 2. So we get 3 times the velocity is 4, we get 12 kilogram meters per second. So this one has more momentum, even though it has less mass, and that's because it's going faster. Anyway, let's calculate where the center of mass is and how fast it's going. So first thing is, let's go ahead and find the x center of mass, the position. So again, that'd be x1 m1 or m1 x1 plus m2 x2. Doesn't matter about the order, it's commutative, plus the sum of the masses. So we get x1 times this, so this would be 5, plus m2 times, so 15. And we divide that by the sum of the masses. So 5 plus 3 would be 8. We get 20 divided by 8. That's 10 over 4, which is 5 over 2, so 2.5. So my center of mass is going to be, there's 1, there's 5, this is about 2.5, so it's right there. Oh, I'm sorry, it's 1, yeah, 2.5. So my center of mass will be right there. Now to get the velocity of the center of mass, we'll do the mass 1 times velocity 1 plus mass 2, velocity 2. And divide that by the sum of the masses, mass 1 plus mass 2. So let's see, mass 1 times the velocity, we get 10, plus mass 2, 3 times 4 would be 12. We sum the masses, it's going to be the same, it's 8. So we get 22 divided by 8. Let's see, that'll be 11 over 8. Should be what, 1 3/8, so just over 1.5. That doesn't seem right. Check my math. 22 by 8. 11. Oops, it's 11 by 4. Bad math. That's why we use a calculator. So it's almost 3, which makes sense. This is 2. This is 4. It's almost 3. Not quite. Because this one has a little bit more velocity, but this one has more mass, so it's kind of pulling it back. So the velocity here would be, what did we say, 11 over 4, which would be 2 3/4, so 2.75. So that's it. The important thing, and it would be in this direction, positive. The important thing is that this doesn't change. This is going to stay constant throughout. So as these are moving, this one's going to move as well. So I have a little demonstration of that. We'll be looking at this again when we do collisions. Let me get that open. Okay, so here we have two objects. This one's just sitting still. This one's going to come over, hit it, bounce back. That right there is the center of mass. So pay attention to that and watch what happens. So you see it's just kind of moving and still moving and it's still moving. And it moves at a constant velocity. Restart. Doesn't matter what's happening. We can even give like this second one some initial, let's give that one some velocity. So we'll say negative 0.5, see what happens. So now these are going to come and hit each other, but watch that center of mass. So it comes, continues. Okay, so we'll be using that. And that's about it for now.